Welcome back to the lecture series in application of nanotechnology in agriculture. So, at this stage of the course, we are talking about the basics of nanotechnology, and in that context, we have talked about the classification of nanomaterial based on their size, geometry, shape, and based on their origin or chemical origin. Post that, we have talked about the different methods of synthesis, broadly the outline of physical methods, chemical methods, and the biological method. And within that, we have talked a little bit in depth about the physical method. So, if you recollect, this is what we have already talked about: the physical, chemical, and biological methods. And within that, we talked about the 5 different techniques: high energy ball milling, pulse vapor deposition, laser pyrolysis, flash spray pyrolysis, electrosplaying, melt mixing, and polymer composite development. And the basic idea what we have discussed in the physical methods of synthesis is that here you are having a bulk material, which I am now shading in red. This bulk material is exposed to different physical forces like lasers, mechanical forces, heat, light, and all sorts of different forces, pretty high temperature, and inside a vacuum chamber the material gets abrated. The abrasion takes place, and that leads to either the deposition or formation of the smaller size particles, and this is essentially a top down approach. So, now our goal will be to explore the second level of synthesis, which is the chemical level of synthesis. So, here we will be discussing about sol gel, microemulsion technique, hydrothermal synthesis, polyol synthesis, chemical vapor synthesis, and plasma enhanced chemical vapor synthesis. So, let us start with the sol gel synthesis, which is a pretty straightforward technique. Sol gel synthesis under the umbrella of chemical synthesis of nanomaterial. Chemical synthesis of nanomaterials. So, in the sol gel synthesis, what we do, there are 2 types of components: a sol, which is a colloidal suspension of solid particle in a liquid. So, basically you have a sol here, which is you are having this colloidal particle all over the place in a liquid suspension. Okay, and what you are having is a gel, which is a polymer containing liquid. So, you have this is your gel, which is polymer containing liquid, and here having colloidal particles in liquid. So, thus this process includes the creation of salts in a liquid that led to the formation of a network of discrete particles or network polymer by the connection of salt particles. So, essentially what you are doing is that, actually I should have picked up a different color out here. Let me kind of modify these colors. That will, these are the polymer particles shown in green. So the idea is, for mixing them, what you are getting is, these are the polymer particles. So polymer particles are getting partly aggregated, and you have different techniques to separate them out by sonication and other techniques, and on top of that the colloidal salts are getting adhered, something like this. So these are the polymeric matrix, and within the polymeric matrix you are having the nanoparticles which are shown in red. Okay, so in other words, this process include creation of salts in the liquid that led to the formation of network of discrete particles. So this is the network of discrete particles, or network polymer by the connection of salt particle. Hydrolysis and condensation are typical steps of sol-gel process, in which the former uses water to disintegrate the bonds of the precursor. That is also the first step in the formation of the gel phase. This process is then followed by condensation that leads to the formation of nanomaterials, after which excess water is removed to determine the final structure of the material. So basically, condensation, evaporation, the basic techniques, hydrolysis and condensation and evaporation, these are the typical processes which are being used in the sol-gel synthesis. So this is the basic sol-gel synthesis, what you needed to understand. So the next technique from here we will be moving is, in this section, is microemulsion technique. Okay, so microemulsion can be defined as thermally stable, macroscopically homogeneous, optically transparent and isotropic dispersions constituting minimum of 3 components. Okay, so what are the 3 component microemulsion techniques have? So it has a polar phase, which is generally water. Polar phase is mostly water, and you have a non-polar phase, generally hydrocarbon, liquid or oil. You have a non-polar phase, which is mostly liquid, hydrocarbon or oil. Okay, and you have a surfactants. The third thing is a surfactants, and we have already discussed about surfactants in the physical synthesis. If you just recollect where we talked about surfactants, here we talked about with surfactants. So these are the surfactants. It could be an anionic surfactants, it could be a cationic surfactants, it could be a non-ionic surfactants, which are kind of helping in not promoting aggregation, reducing the surface energy and reducing the size. There are 3 things what a surfactant does, and here also the same principles of surfactants will apply. The surfactant which will ensure that, so say for example you have, now if you have to understand microemulsion, it's something like this. Say for example you have this polar phase, which is water, and in that you have oil phase, which I am showing in which is immiscible in water. This is the non-polar phase. This is the polar phase, which is water. Then you have a surfactants, which I am representing with, say, green color, which is this. And now you wanted to synthesize a particle, say for example some particular particle you wanted to synthesize, and that material is in colloidal suspension, like out here, which is red. So you wanted to create a nanostructure of these ones. which is nanomaterial to be synthesized. Okay. Now, say for example, you take this whole mix and you sonicate it, or you give some kind of forces by which it will create an agitation out here, okay, some form of an agitation which is happening either by, say sonication or shaking or somewhere or other. You are creating and agitating the molecules. So what will happen is these non-polar phase, these ones, they will try to self-assemble. So something like this will arise out of it. These non-polar moieties within the liquid. So this is the polar phase, which is water. Within water, these non-polar moieties will form some kind of a spherical in order to reduce their surface energy. And within that, you will have the surfactants which will ensure they remain separated from each other. And since during agitation, randomly, some of the particles will get trapped inside. So in other words, each one of these sphere, what you are observing out here, is acting as a nanoreactor, nanovessel. Now at this stage, if you evaporate the water out or lyophilized or do something to get rid of the polar phase, so what you are left with is this. So your water is gone, water removed. What you are left with is something like this. And you can control the size by what kind of force or what kind of temperature you are allowing this reaction to occur. And some of the polar moieties may get trapped or may not get trapped depending on what level of evaporation or lyophilization you are doing. So this is the second technique, which is a fairly low temperature technique mostly, and pretty commonly used and pretty popular among the people who work in the area. So surfactant molecule thus creates the interfacial layer separating the aqueous and the organic phases, reducing the interfacial tension. So this is what the surfactants is doing. So out here it is reducing the interfacial tension, okay, creates the interfacial layer separating the aqueous and the organic phase, reduce the interfacial tension between the microemulsions, and the excess phase act as a steric barrier preventing the coalescence of the droplets. So it also prevents these droplets, to coalesce together. Microemulsion system consists of monodispersed spherical droplets of the diameter ranging from 800 to 8000 nanometer of oil in water or water in oil, depending on the surfactant used. And with water in oil, reverse micellar system acts as excellent reaction site for nanomaterial synthesis. And reverse micelle is water in oil microemulsion, where polar head groups of the surfactants creating the aqueous core and resides towards inside, whereas the organic tail of the surfactant molecule directed outside. Okay, so you could have a reverse micelle, you could have normal, depending on whether it is water in oil or oil in water. Okay, in general, there are two microemulsion routes to synthesize nanomaterial synthesis. One is microemulsion methods and two is basically water in oil and or oil in water, okay, as I have mentioned earlier. These are some of the very, I should say, non-energy intensive processes if you compare a microemulsion with respect to any of the physical methods what we have already discussed earlier. So, you can understand that these kind of techniques does not require heavy machinery or high energy, and yet they are very user friendly techniques for most of the labs who work on nanomaterials. Okay. From here we move on to the next synthesis, which is we are moving on to the hydrothermal synthesis. So, hydrothermal synthesis, if we look at, it's a method used for the fabricate of nanomaterial of metal oxides. Mostly it is used for, okay, now we are into hydrothermal synthesis. So, hydrothermal synthesis is used to fabricate nanomaterial of metal oxide, iron oxide or lithium iron phosphate, keeping control over the characteristics of the particle by varying the properties of near or supercritical water by using different pressure and temperature condition. As it says, so there is this parameter pressure. So, depending on what kind of pressure you are giving and what kind of temperature, thermal and pressure, these two parameters in the presence of how much water you are keeping into the system, near or supercritical water, by using different pressure and temperature. So, you have three parameters: water, pressure and temperature. This is the interaction of these three which dictates the hydrothermal synthesis, but this is again a high energy system. Hydrothermal synthesis requires pretty high energy. Okay. So, it can be performed in two types of system: a batch hydrothermal or continuous hydrothermal process. The former is able to carry out a system with the desired ratio phases, while the latter allows a higher rate of reaction to be achieved at a shorter period of time. So, this is another technique which is pretty commonly used in different polymers and different metal oxides. Okay. Next, we will move on to polyol synthesis. So, what is polyol synthesis? Polyol synthesis is basically the synthesis of metal containing compounds using polyethylene glycol, PEG. Use of polyethylene glycol. Ethylene glycol. So, use of PEG as a reaction medium that play a role of solvent, reducing agent, complexing agent at the same time. So, the role of PEG is as reducing agent, complexing agent, reducing agent, complexing agent. At the same time, it is acting as a reaction medium, okay, and plays as a basic solvent. So, it has multiple role to play in the polyol synthesis. This chemical process was used to synthesize wide range of metal based nanomaterials of like silver, platinum, palladium, copper, several metal oxide like zinc oxide, indium tin oxide, gadolinium oxide, different magnetic nanomaterials, so on and so forth. So, as we will move through, you will realize polyethylene glycol is used for several delivery systems apart from being used for different kind of metal or metal oxides metal oxide systems. We'll come later into that once we'll be using. So here you should have an idea that what these synthesis or these terminologies really mean to you. But when we will come to the real synthesis or real application, we will talk about for these particles we can use these kind of synthesis, for this particular particle or this kind of nanomaterial we can use this kind of synthesis. Okay. So now from polyol synthesis we move on to the next one, which is chemical vapor deposition or chemical vapor synthesis, which is again on the same line as physical synthesis. So chemical vapor deposition, CVD, and chemical vapor synthesis. Okay. CVD or CVS is a process which is often used for deposition of solid films from the vapor phase. So you have something in the vapor phase, as we mentioned in the physical synthesis, something in the vapor phase, you are depositing it on a substrate. It's kind of used for all sorts of thin film deposition on a substrate. Most likely we use for thin films synthesis. Okay. So thin films produced by CVD processes at certain conditions also contain ultrafine particles. Hence, the synthesis of nanomaterial can also be possible by this method if CVD system is modified. Say for example, you have high temperature in hot wall reactor, high supersaturation or low residence time and a small substrate. If you have all these parameters and you really wanted to use very small amount to synthesize nanomaterial on a substrate, then the best idea is to follow CVD. But the problem with CVD is the very moment you move to CVD, CVD demands a lot of intensive instrumentation and high pressure requirements, vacuum requirements, and several other complex technical know-how is essential for chemical vapor deposition. Okay. So from CVD, so we are into chemical vapor deposition and plasma enhanced chemical vapor deposition, which is the last one. Plasma enhanced chemical vapor deposition is pretty much a further modification of this, which is plasma enhanced chemical vapor deposition. So basically, plasma enhanced chemical vapor deposition, also called plasma assisted chemical vapor deposition, is a popular CVD process, which is chemical vapor deposition process, which is widely used for the deposition of thin films. And plasma enhanced chemical vapor deposition process can also be used for synthesis of nanomaterial. As the name suggests, the plasma enhances the chemical reaction. So you are using plasma as that force, just we are talking about the physical forces, which is enhancing, basically plasma enhancing the nanomaterial, is giving sufficient energy, enhances the chemical reaction for the synthesis of thin films and nanomaterial. So when we talk about such processes, as I was mentioning earlier, you will be needing a vacuum processing unit. So these are those requirements. A vacuum unit you will be needing, then you will be needing a very high power supply, you need a gaseous precursor. So in other words, okay, then you need pretty decently high power supply, and you need pretty specialized apparatus to have this plasma enhanced chemical vapor deposition to take place. So you realize that these processes, which are as of now we have discussed the chemical and the physical processes. They are the ones which help in initiating the field. But now slowly we are realizing much of these techniques require extremely high energy and needs very specialized training. On the contrary, if we try to emulate nature, the way biology has done things, we may be able to make a very different industrial development or very different kind of industry for nanoparticle or nanomaterial synthesis by using biological route. So that will be our next target, while we will be winding up the nanotechnology, basic nanotechnology section, and from the biological routes we will move on to the application part, which will be much more easy to slowly bringing down the energy of synthesis and then moving into the agricultural domain. So I will close in here. So our next target will be understanding the biological route of nanomaterial synthesis, which in the current context of sustainability, sustainable development, is much more relevant to us in terms of delivery of agrochemicals, release of agrochemicals in the agricultural sector, and as well as boosting the economy of small scale industries which can achieve these things, who do not have such sophisticated instrumentation as well as very high infrastructure. Okay. So with this I will conclude, and the next class will move on to the biological synthesis of nanomaterials, the future, the sustainable future. Thank you.